Not a girl.
I was just trying to go back.
That's a bad idea. On lockdown, I'd be like, taking my chances and staying in the bathroom.
That's where you stand up. Like try to hide.
I think that's literally what you're supposed to do.
So let's get back to work. Well, Landon will just have to deal with it. But we're just hang out not away for a while. Alright, so anyway, yeah, so the focal point for a convex mirror is actually back here. And it's virtual. And you notice I drew dashed lines? So the theme here is going to be when light is where it should be, we're going to use solid lines. And those lines are going to be real light. When light isn't where it should be, or when you need to draw something behind where the light is not, we're going to use dashed lines, and those are going to be virtual lines. Okay, makes sense?
Yeah.
Alright. Now, of course, let's do the same thing. Let's take our flat mirror. Let's now have an object. We'll have the object will be illuminated by the environment. 3 lines with the object. Light will go past and create a virtual image. These should actually be dashed lines, unfortunately. Those should actually be dashed lines. So that's a virtual image behind a flat mirror. The lights actually, these lines actually should come back and these should have dashed lines, but I haven't fixed it. Concave mirror, light goes in, and then the rays converge. Now, if you put the observer here, then your image is going to be inverted. If you put your observer inside the focal distance, then your observer is going to see an upright image. Okay? So this is going to be our focal distance. And if you have 3 parallel lines coming in, you put your observer beyond the focal distance, they're going to see an inverted image. If you put them inside the focal distance, they're going to see an upright image. Now, we're going to add several layers to this process in a little bit. You have your convex mirror, same object. Light diverges, and we trace back. Once again, these should be dashed lines. Dashed lines, but I need to fix it. And it's going to produce a virtual image, an upright virtual image. Okay, how are we doing so far? Make sense? Yeah.
So a flat mirror will not have a focal point.
Correct. Well, a flat mirror has a focal point of 0. Basically, it's at the mirror.
Okay.
Shall we move on? Not moving on. Okay. Again, these should be dashed lines, dash, 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 dash. These should be dashed lines. But I have not yet fixed it in multiple years. It's just not a priority for me. Okay. Shall we move on? All right, when we're talking about things being in front of a mirror, the object is always going to be in front. When we're talking about things being in front of a mirror, the object will always be in front. The image may be behind the mirror or in front of the mirror. If an image forms in front of the mirror, it's a real image. This is the real side of a mirror. In other words, if the light is where it should be, bouncing off the mirror, then the light is real. If the light is not where it should be, it is virtual. Okay? This is the virtual side of all mirrors. Light bounces off a mirror, so this is the real side of all mirrors. This is the virtual side of all mirrors. When we say something is behind a mirror, we're talking about on the opposite side of the object. Okay, there is some math, of course. It's actually kind of neat math. There is some math. This is the mirror equation. 1 over f equals 1 over do plus 1 over di. F is the focal distance of that mirror. Do is the distance of the object, and di is the distance of the image. We're going to use this a lot. A lot. This is a very, very handy formula that allows us to give us lots of information. Be advised of the fractions. Be advised of the fractions. I don't know where the reciprocal key is on these calculators.
This concludes the soft lockdown drill.
So I just go 1 divided by answer. That usually gives me a reciprocal. Landon's probably hanging out in the other classroom. Or huddled in a corner. Okay, now I do not know entirely why we don't just reduce the focal distance to 1/2 r. Why we don't just say it's 1/2 r. I know it has something to do with the index of refraction for lenses, but I don't know why they just say f is 1/2 r. But it is. So if you have a radius of curvature that is 10 centimeters, if you have a radius of curvature that is 10 centimeters, your focal distance is 5 centimeters. Okay, can you see this in your head? Can you see that 2 over 10 is the same as 1 over 5? So if your radius of curvature is 20, then your focal distance is 10. Focal distance is always 1/2 r. But that's the way it's shown in textbooks. I don't know. It just is. All right. So, magnification. Magnification is a ratio of an object's image, or the size of an image to the size of an object. Hi over ho. It's also negative di over do. Why negative? You'll figure it out next week. It has to do with virtual and real images. Virtual images get a negative sign. They get a negative di. Objects are always real. Do will always be positive, always, 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 always. Di can be negative, and f can be negative. You can have a virtual focal length, but you cannot have a virtual object. You can have a virtual focal length, and you can have a virtual distance of image, but you cannot have a virtual distance of object. Objects are always real. So in our little diagram here, this would be the height of the object. This would be the height of the image. The magnification would be the height of the image over the height of the object. Looks like about 1/3. 1 over 3. Distance of the object from the device, distance of the image from the device. Yes?
What are virtual images used for?
Making things tiny.
So, it's a real thing?
Well, the light has to go somewhere. So when I say virtual and real, what I don't mean is existing and not existing. What I mean is the math works differently for a virtual image. So the light definitely does something. It's just the light is diverging. But we have to make sense of the light. So we say, oh, you have to basically take the diverging lenses, trace them, or diverging rays, trace them back, and create a virtual image behind the mirror. Again, this is one of the weirdest things about optics, is using the word virtual to mean it just puts the image is somewhere else. It doesn't mean it does not exist. It just means it's somewhere else. The light is doing some different math. Okay, other questions? And we'll move on. Okay, so some types, we talked about reflection. The law of reflection applies when media just bounces off a new medium. Refraction occurs when we change speed. This is what happens in a prism, or when light travels through a lens, or when light travels through your eyeball. Refraction is just a changing of speed. This is that double convex lens that I had. Yeah. Go ahead.
One of my science teachers told me that refraction is the bending of light.
Yep.
Is that incorrect? Or?
No, that's right. It's bending because it's traveling at different speeds. Different parts of the image is traveling at different speeds. So when you have a convex mirror or a convex lens like this one, it's fatter in the middle. So when light comes in, it's traveling slowest where it's fattest. That causes light to bend. But it comes about because of a change in speed. Now, diffraction is a little bit different. Let's see how bright today is. Let me see. Maybe. Diffraction occurs when you bend light. When light bends around things. It's usually used in, like, you have two really close razor blades, put them really close together, and you get a little slit of light, and you can see the light bending around things. There's some pretty cool diffraction phenomena that we're not going to investigate this year, just because it's beyond the scope of this course. But we're going to primarily focus on refraction in our first year course. And refraction is the changing of speed, wave energy. As wave energy changes speed as it goes through a different medium, then it bends. Diffraction is a different kind of beast altogether. It basically is bending around large objects. That's diffraction. Really quick. This is a good example of diffraction. Light waves can come in flat, and then they can bend at corners as they strike these corners, and that can cause them to bend into circular waves. Again, and this is all I'm going to talk about it this year. Next year we'll spend some more time on it. Okay, that's a good place to stop. We'll pick this up again tomorrow. You can play with the mirrors.